You know, in computer science, some of the most powerful tools are also the most elegant. Today, we're diving into one of my favorites, the Disjoint Set Union, or DSU. It is the secret weapon for tracking connections in these massive, sprawling networks, and its speed is, well, it's almost unbelievable. Let's see how it works. All right, let's kick things off with a problem. Imagine a social network with, say, a billion users. Now, how would you check if person A is connected to person Z? Not directly, but maybe through a long, winding chain of friends of friends of friends. Answering that question in a fraction of a second, that seems almost impossible, right? But that is exactly the kind of challenge DSU was born to solve. At its core, that whole social network problem is really all about one thing: keeping track of groups, or if we want to get technical, disjoint sets. And once you start looking for this problem, you'll realize it shows up absolutely everywhere. I mean, this isn't just about who knows who on social media. The exact same pattern pops up when you're managing computer network connections or when you're identifying clusters of pixels to form an object in an image. It really all boils down to managing who belongs to what group. And this is where our hero, the disjoint set union, finally enters the picture. It's a data structure that was custom built for one job and one job only: to efficiently manage a collection of groups that don't overlap. It's designed to do two things, and to do them exceptionally well. The whole power of DSU really comes from two simple core operations. The find operation answers the question, hey, who's the leader of this group, by finding a single representative for any member. And the union operation, well, it does exactly what it sounds like. It merges two separate groups into one. They seem like simple questions, but answering them fast is the whole key. So how would we actually implement this? Well, the most intuitive approach, the one you'd probably think of first, is pretty simple, but it has a really serious flaw. See, if we just randomly link groups together whenever we do a union operation, we can end up with a structure that looks like a long, spindly chain. Seriously, just picture a conga line. To find the leader at the front of the line, someone at the very back has to tap every single person in front of them, and that is incredibly inefficient. So here's the crucial point. Searching that conga line could take O of n time. That means the search time grows linearly with the number of people in the group. For a network with millions of users, that's not just slow, it is a complete deal breaker. We need a better way. And that better way comes in the form of two brilliant optimizations, two magic tricks, really, that transform DSU from this slow, flawed idea into one of the fastest data structures we have. The first trick is called path compression, and it's such a clever idea. It means every time you perform a find operation to go locate the group's leader, you do a little bit of housekeeping on the way. Okay, so here's how it works. When some element needs to find its leader, it traces the path all the way to the top. But then, and this is the genius part, as it returns, it makes every single element it visited on that path point directly to the leader. It's like creating a super fast shortcut. The next time any of those elements look for the leader, bam, the answer is just one step away. The tree literally flattens itself over time. The second trick, union by rank, is all about being proactive. It's a strategy to keep our trees from getting too tall in the first place. We just keep track of a rank for each tree, which is basically an estimate of its height. And the rule is simple. When you're merging two groups, you always attach the shorter tree to the root of the taller tree. And the effect of this is dramatic. Just by following that one simple rule, we make sure our tree structures stay as shallow and bushy as possible. We actively avoid creating those long, inefficient conga lines by design, which keeps our find operations fast right from the get-go. So we've got these two really powerful ideas, but let's see how they actually translate into code. You might be surprised. Believe it or not, this single line of C++ code, that's it. That's the entire implementation of path compression. As the find function recursively calls itself to find the group's leader, this little assignment right here relinks each node's parent pointer directly to that leader on the way back down the chain. It's just incredibly elegant. So what happens when you combine path compression with union by rank? What kind of performance you get? You get this: O of alpha of n. This is the big reveal. This right here is why DSU is so legendary. So what on earth is alpha of n? It's the inverse Ackermann function, and it's a function that grows so mind-bogglingly slowly that for any realistic input size you could ever throw at it, we're talking even the number of atoms in the known universe, its value will never reach 5. So for all practical purposes, this means our operations are effectively constant time, They are almost instantaneous. With that kind of speed, it's really no surprise that DSU isn't just some academic curiosity. It's a workhorse that powers some of the most important algorithms out there. For example, it is the critical component in finding the cheapest way to connect all points in a network. That's Kruskal's algorithm. It can instantly detect if adding a new connection would create a loop, or a cycle, in a graph. It's used to identify distinct objects in an image by grouping together all the connected pixels. It's a truly foundational tool in computer science. So, to wrap things up, let's just go over a quick cheat sheet to make sure that when you go to use DSU, you get it right. The single biggest takeaway is this. Always use both optimizations together. They're a team. For best practices, just remember to initialize each element as its own parent. Use a flexible data structure like a vector to store your sets, and make sure your union logic correctly updates the ranks. Following these rules will help you avoid all the common mistakes and really unlock DSU's full power. And that's the disjoint set union. It's two incredibly clever optimizations that solve a massive problem with just breathtaking speed. It's a tool that empowers us to analyze these incredibly complex networks. So the question I'll leave you with is this. Now that you have this tool, what problem will you solve?